So also I wanted to point out, I forgot, the so I have my regular office hours on Wednesdays from well, it's 4 to 5 Central Time, so 5 to 6 Eastern Time. So basically, half hour before this class starts. But you can also schedule one. You can just send me an email, but you can also find a link to a scheduler that is in the news forum. I think at the beginning of the semester, I sent one out about office hours, and it includes the link there. Maybe I'll cut and paste that and put it as a separate link in Moodle. But if you go to Moodle and you go into the news forum and you look at office hours, you'll find a link that you can do to schedule an ad hoc appointment with me, and that is available on Monday, Tuesday, Thursdays, and Fridays. So Wednesday, if you want to meet with me Wednesday, try to do the regular office hours, because the rest of the time I'm prepping for class. So hopefully that works for everyone. All right, so let's try to finish up on this chapter and look at reinforcement learning. So screen 2. Okay, so we have looked at the high-level behavioral planning, and we've looked at or behavioral decisions. We've looked at motion planning. Now we want to look at how do we actually make that happen. Now, we'll do that using a process we call feedback control. Ultimately, the feedback control module converts motion commands into signals that move actuators, right? So we want to move to these trajectory points, and so at a certain speed, right? And so now we've got to figure out how much voltage do we apply to the drive motors, or to the brakes, or to the motor that turns the steering gear, type of thing, right? So the goal of a control system is just high level. It's not a mathematically accurate type of thing, right? But it's more of a heuristic goal of a control system is to respond to the inputs, including possible disturbances, and force the output to the desired condition. And we typically want to do that as quickly as possible while maintaining stability and possibly avoiding overshoot. So that's super high level. If you've had a control systems course before, you're gonna scream at me saying, "Oh, that's crazy," right? So there's all sorts of factors on how we really measure it, right? But I know that senior double E's, undergraduates, normally take the control systems course next semester. So you haven't had these concepts, or at least had them in much detail or depth. And if you're computer engineering undergraduate, well, you probably never take feedback control, I don't think. So so we're going to try to handle these concepts at a pretty high level. Again, apologize to the grad students. There's really not much time to cover these concepts in depth anyway, but also don't want to want to try to bring everyone along at a reasonable pace and not lose anyone. So but what do we mean by stability and overshoot and that type of thing, right? So stability is roughly describing the our ability to avoid the situation where we might have positive feedback. Maybe you studied this in your circuits course. if you have positive feedback in an amplifier, then your output will grow without bound. Well, it's subject to the power supply, but so we want a system to maintain stability and not get into a regime where we might have a lot of let's say our feedback signal is delayed or something like that. I'm trying to think of how I can explain stability without going into all the details of it. But overshoot, the best way we think about overshoot typically is you look at an airplane landing, and it wants to approach that runway and just touch down very smoothly, right? We call that kissing the landing. You don't want to overshoot the altitude on the landing, because that means you're going into the ground. So you want to just approach it very slowly. It's sometimes beneficial to allow some overshoot, because typically you can get to a situation where you're matching the desired output faster if you overshoot a little bit and then zero in on your target. But in other cases, physical constraints of the system says you better not overshoot. So here's a super high level diagram that we often look at. You may have seen this, as I say, in your circuits class when you're or electronics class when you're developing amplifiers, and maybe you looked at how adding a little bit of feedback might trade off gain for bandwidth and linearity and that type of thing, right? So but generally, we've got some sort of system that we're trying to control, and we might designate that as G of S. And we've got this, feedback network that's sensing the output, maybe is filtering or compensating for some of the errors. We compare the input, input desired signal to this signal, and that produces an error value, right? And then that error value goes to this system and tweaks it. And so this system is designed to run that error to zero, right? And that is matching these two inputs. So super high level. So maybe a little bit more detailed of a circuit here. Again, we still have the input. We've got a comparison block here, and that generates this error signal. And that goes into our controller, right? And now here we've actually have shown our system that we're trying to control. And that could be our drive motors. We might want to drive those in forward or reverse at certain speed, and it takes a certain voltage applied to them to make that happen, right? Or we might be actuating our brakes, or we might be controlling our steering motor, right? And this system has some disturbances, right? So that might be bumps in the road. It might be a hill, or could be friction, could be wind, or all sorts of other things that might represent something that disturbs our normal operations, right? And so those disturbances will result in an output that's a little bit less than what we desire. And so when we sense that and we compensate for it, we end up with this error signal, right? So kind of answered some of the first question there. But how would you design the system for acceleration, braking, and or steering, right? So, we would need to measure our speed, and or in the case of braking, we want to measure our deceleration type thing. We might measure our steering using a heading indicator, a compass, electronic compass, or maybe a gyroscope. We talked a little bit about, I think, when we were looking at Kalman filters and IMU, that could look at accelerations in X, Y, and Z dimensions, and also using a miniaturized gyroscope, it can look at rotations in terms of pitch, roll, and yaw type things, right? So you might have a sensor that is measuring those effects and feeding it back, and also. All right. Then we have this system model here, right? Whether it's this G of S or is this system along with the controller. How do we find a system model? Well, oftentimes we assume what is known as a bicycle model. We kind of looked at this near the beginning of the course, but just kind of hand waved it through. It looked at steering of vehicles. Here we're going to assume that it has the vehicle's a rigid body. That's a pretty good assumption, with front and rear wheels connected by a rigid axis. And we're going to assume that the front wheels can rotate freely within a certain angle, right? And so we're steering by the front wheels. Not every autonomous vehicle is this way. It can be a tracked vehicle, which I've done a little bit of work with, or all four wheels might be steered, that type of thing. So this is not the only model, but this is a very common model, and certainly one we're familiar with consumer cars. So our back wheels cannot rotate in terms of its steering angle, and are parallel to the body. So the consequence of assuming this model is that to move laterally, you must also move longitudinally. Right? So we can't move, pivot all our wheels and then move just laterally. We've got to move, pivot or rotate our front wheels and then move forward, and then that will take us in an arc, right? So here, the book goes through some equations and that type of thing. We're going to skip over that, but here would be your rear wheel, here would be your front wheel, and we have an ability to describe those mathematically. And from this type of coordinate system, you can write equations that will show you for a given angle what is going to be your turning radius or curvature of the path that you're going to trace out, and that type of thing. And so you can, from here, you can take and note that there's motors that pivot or rotate this wheel in this delta angle here, and you can relate that to the angle at which you want the car to be running and that type of thing, right? So, all right, so now how do we actually control it? I'm just going to toss this out. If you're taking the control systems course, you probably don't get to PID until later in the course. Here I'm introducing it like 3 slides after I started talking about control systems. So understand there's a huge leap to get to designing one of these things, right? But we're going to toss it out there. PID, super common control system, pretty pretty straightforward, but it includes both proportional, integral, and differential arms. Represented here is the proportional. Here you are multiplying your air signal by a constant, okay, and then adding that as a control signal to your plant or process. And that works on its own, but you can have some residual error depending upon the system model of your plant or your process. In our case, this is our car, right? And so to kind of eliminate those residual errors, we add an integral arm here. And now we integrate this error over this period and multiply it by another constant k. And that accumulates the error and therefore does a better job of driving the total error to zero. And then we can also add a differential arm here, where now we're taking the derivative of the error. And this is useful when we start seeing the error have a large rate of change. When we've had a big disturbance here, let's say, and all of a sudden we're really going off in terms of error. That means if we have a high rate of change, our derivative will be large. We multiply that by that k, and this term, this derivative term, will dominate and steer the plant back to its control point. So this is able to respond quickly to, as you might expect with the nature of differentials and integrals, right? Is that this differential is going to respond quickly and help your response time, your settling time. And this integral arm is going to help with the long-term error. And this proportional arm is kind of doing your heavy lifting. It's doing most of the work most of the time, and these guys are kind of finessing it along the way. So hopefully, if you haven't had any exposure to control systems, hopefully that makes sense, right? But you've got some input control. It in a regular manned car, this might be your accelerator pedal, or it might be a steering wheel, or the signal coming from that actuator. And then all of this would be your propulsion system, or your steering system, or your braking system, right? And then all of this would be to make sure or match that the output is doing what the input's telling it to do. Okay? So, and you can think of this as like, yeah, if you set your cruise control is trying to keep you at a particular speed, right? So that setting is getting adjusted there, and then all this magic happens to make that happen. So, so the PID control system is consists of this proportional, integral, and differential arms, and common technique to quickly drive the tracking error to zero. Typically implemented, even though this, I think I cut this out of the author's textbook, or maybe I got it somewhere else. You see it's got T's here, right? So that kind of would imply a continuous time system, but typically we implement this as, in these days, as a digital control system. So there'll be a sampler out here sampling the plant and process, and maybe quantizing it, and so digital control systems kind of have an additional set of analysis, and typically we would call our time parameter now n as the sample of time instead of T implies continuous time. And S, you may have seen S in my previous diagrams here. I have S there. That's because we typically analyze our continuous time control systems using Laplace techniques. So we're in the Laplace domain and we use the letter S, but when we work with digital control systems, we're typically working in the Z domain. So don't worry about it now. If you haven't had control systems, that's the last you're going to see it on this lesson, but that's the idea. Now, one last thing is there's also this model predictive control. I think one of y'all is doing a project that involves model predictive controls, so it's worth mentioning here. So conventional PID controllers handle one input and measurements from the past, okay, and hopefully not too far in the past either, because when you're doing this feedback, this needs to be pretty fast, right? If there's some delay in this feedback path, then that's when you can end up with a lot of stability problems, because you're correcting for something that occurred in the past. And if this thing's like oscillating a little bit and you measure it with this feedback signal, maybe when it oscillates to the let's see if I can draw this out. Just if you're measuring it there, but then by the time you do this whole feedback and all this stuff, that and you conclude that, well, we need to have a signal that forces it down, right? Because it's, you want to be right there, but so we're above, so we're going to send a signal go down. But if by the time you emit that signal, the system has kind of moved on and is oscillated down here, now we're going to be adding a down signal to a signal that's already down and actually going to be amplifying the adverse effects, right? So a delay like this can really hurt us, right? Equivalent to phase margin or something if you've studied this, right? So, but just in a super hand wavy way. If we have a system where there's just some delay, maybe we got trying to think of a scenario in autonomous vehicles, but in some cases you've got a long distance between your physical system and where you're controlling it from, if it's like a remote controlled type of thing. And so that propagation time could add a delay. So back to model predictive control. So PID controllers struggle with more than one input parameter and can't really predict the future, and can, even though I didn't write it here, can also struggle with feedback paths that have a lot of delay or delay in the system. So MPC systems can solve these problems potentially. So they can handle multiple inputs and constraints. MPC can also, because it's really based upon a model that it's predicting, right? So we might have the physical system out here is this vehicle, but we have a model of the vehicle in this controller, right? So we've maybe made a bunch of measurements on this thing, or made some theoretical calculations, and we've derived a model. Then now we've got an optimizer. We can take these inputs, these measured outputs, and what we're trying to, our inputs, our reference, and we can plug that into this controller, and we can run it through this model and optimizer, and then output these control inputs. So if we've have a bunch of inputs. Well, we can put them all into this big model here, and this optimizer can be a multi-constraint optimizer, and then produce multiple control inputs to this vehicle. It can, because it has a model, it can potentially predict the future, right? So if we have maybe a trajectory type of situation, it can predict what's going to happen in the future and start to make controls associated with this, right? So, and if you're have a long delay associated with this, well, you can model that delay in this system here. So I added a link here that you can look at if you download the presentation from Moodle, and can click through on that. So yeah, think about how this might be advantageous in UAVs, and maybe read that article. Maybe I'll put that. It's actually not even an article. It's like one of these kind of online things. I don't know if it's from Medium. Maybe it's from Medium. So I take it with a grain of salt. But I just found it real quickly and decided to toss it in there for your review. So let's take a step back and just take a few minutes here and think outside the box. You know, if you watch the financial news, you're paying attention to the economy, you know that we had this period of high inflation. The Federal Reserve is the organization that is responsible for trying to control inflation. They have a target to keep inflation at or below 2% per year. Some inflation's good, but because it makes it easier to pay our debts in the future, and it's reflective of economic growth, blah, blah, blah. I'm not an economist, so don't trust me on all that. But they measure all these economic data, right? We have all these government offices that look at number of unemployment filings. Businesses report certain inventories and certain activities and that type of thing, right? So there's all these guys and gals out there collecting all this data, and they publish these reports, and they typically, you know, maybe publish it once a month. Maybe that data is 2 months old. Maybe they publish it once a quarter. So the Federal Reserve then meets periodically and tries to make decisions on what to do with the interest rate. And that interest rate is what's trying to control our economy. And it's only one factor in a whole bunch, right? So our economy has all sorts of disturbances associated with it. If there's a new war, there's oil price, you know, outside of our control in the Middle East or something like that, where OPEC decides to limit production, and so the oil prices will go up. All these things have effects on our economy, and the Fed is always working with data. It's not a very observable system. So they can only partially observe. No one knows exactly how many people are looking for work. No one knows exactly how many products are sitting in warehouses that have yet to be sold, that type of thing, right? So it's a partially observable system, and has a lot of delay associated with it, but also has, in the case of the Fed, they actually have this dual mandate. It's a little bit controversial. Not every federal banking system in other countries has this dual mandate, but their dual mandate is to provide for full employment. So they want to control the economy so that basically everyone that wants a job can get a job, you know, obviously within reason. And so they have a number. I think it's like 4% that they say is 4% unemployment rate is what they consider full employment, and their target is 2%, right? So there's two inputs, right? So You can't use a conventional PID controller there, and we'd like to predict the future because we that's what we're interested in. We're interested in it today, but we're also interested in what trying to control the economy in the future. And we've got a lot of lag in the system, right? So just trying to draw some analogies. Those type of things really help for me to understand things. I know I'm not going into a lot of depth, or actually any depth, on the mathematics of these things, which is kind of normally we would do that in graduate level courses, but trying to get through a lot of material and try to deal with a lot of varied backgrounds. So toss out analogies to kind of help you understand things when we don't have the math to do that. All right, so a bunch of that. Let me switch out of this. Yes, I want to keep those. Not sure why, but and let's start looking at reinforcement learning, and going to introduce some concepts here. And I'm restructuring the last part of this course kind of on the fly. Part of that is based upon that survey we did right at the beginning of course, where we, where I asked, what's your knowledge, background, what things do you know? This course doesn't have any prerequisites, but maybe it should. But if we had too many prerequisites, then it would be kind of impractical and no one would be able to take it, right? So, because you really need a lot of different backgrounds to be an expert in everything about autonomous vehicles. I'm not an expert on everything about autonomous vehicles. You probably figured that out by now. But so we did that skills survey, and so I'm kind of adapting the course based upon that, based upon how the progress we're making and that type of thing. So I think we're going to spread reinforcement learning out to a couple of lectures, and also hopefully go back and look at some more practical Python examples. I've gotten a little bit of ad hoc feedback that you guys like that when I give you a little bit better context and actually talk about implementation, that type of thing. So, some of the last lectures I always kind of have a little fuzzy anyway. We'll still try to talk a little bit about how systems, other systems like naval systems or space systems and that type of thing, and just talk about those, but we can cover that pretty quickly. And I like to leave the last lecture to certainly as a semester review, but also to talk about current research. You're getting a good background in current research and doing your research reviews, so we'll speed over that. So expect to spend next week on reinforcement learning, and then maybe some time after that, I think we're also going to look at edge computing and the ROS robot operating system type of thing. And so we'll try to cover those also, but we'll look at some more practical examples, and we'll try to go back and maybe look at object detection in a little bit more practical approach. Actually, do some training live type thing. All right, so that just kind of gives you a little bit of looking in the future here. So not sure I'm covering all of this other than maybe mentioning it, but let's just dive in here. So reinforcement learning framework here. Well, what is reinforcement learning? First of all, we're trying to learn by exploring an environment, and it's a lot of the way we humans and higher mammals learn. And yes, we're maybe born with some instincts, but we begin exploring the world, and we do things, and some things work out and some things don't work out. When things work out, we get maybe a reward, right? If we're a baby and we cry, maybe we get fed. If we're a toddler and we start reaching up to touch that hot burner on the stove, maybe we get yelled at, or our hand gets gently slapped or something, right? So there's a negative reward in that context. So we're exploring an environment, and we're learning, and our good choices are reinforced, and our bad choices are kind of reinforced in a negative way. Right? So that's what reinforcement learning. You recall that we talked about supervised learning, and that's the object to image classification, object detection, and image segmentation, and what our neural nets normally do, including fully connected neural nets and convolutional neural nets. All that type of thing is where we present a network with like questions and answers, right? The inputs and the outputs, or the labels that we expect, right? And then we train that network to produce that, right? That's supervised learning. Unsupervised learning, we only mentioned ever so briefly. And that's where you might do some cluster analysis. You might look at how data actually kind of clusters, but maybe you don't even know what that cluster is or means or something, but you figure out that it clusters in certain ways. So that's unsupervised learning. Reinforcement learning is kind of your third major class of learning. Right? So we have an environment and an agent. So our agent is what is exploring the environment. Right? And so we have this concept of states, actions, and rewards. We already talked about that at the beginning of this lecture, right? With the Markov decision process and that type of thing, right? So we have a state T. We're evolving to a state T plus one by taking action, right? So learning takes place in rounds. So we're going to do this T plus one, T plus two, T plus three. Our agent perceives a state and reward and chooses an action which it thinks will put the environment into a new state, which will maximize its reward. In most cases, in many cases, the agent doesn't even know what it's trying to accomplish. It just knows it wants a reward, right? It doesn't know that if it's a car that it's trying to stay in its lane and drive as quickly as possible, but still under the speed limit, right? But that reinforcement learning agent in there is just knowing that it wants more reward, and that's how it's motivated, right? And so it takes these actions, and that puts us in a new state, and it receives some reward associated with getting into that new state. Right? And so was that action taken a wise one, given the state that it was in, or not? Right? So so we want to remember that in some way in order to find the best action next time. So here we go again with the Markov decision process. So the previous slide describes a single move game. So how do we handle situations where the agent must make a series of decisions in order to reach its ultimate goal? So a Markov decision process helps us model this scenario by formalizing sequential decision making. So here we're going to go a little bit deeper now, a little bit more rigorous. Assume a discrete set of states, actions, and rewards at discrete times. At time step T, the agent receives a representation of the environment state. Okay, so at time T, the environment's telling this agent through sensors or something Right? This is the state of the environment. So that's an input into the agent. And that's some state at time t out of some set of states that are possible, right? The agent selects an action A at time t out of some set of actions. And we track this as a state action pair. So you'll see this a lot. So we'll have the state at time t, and now we're going to take the action at time t. So this time is now incremented to t plus 1, and the environment transitions on, behalf or bequest of this action here. It's going to transition to a new state, st plus 1, still out of this set of states due to this action of at, or and other external or random effects, right? So it's a hint that it's not always deterministic, right? We might have things messing with us to go to a state that maybe we thought we were going to one state and we ended up at a different state. So the agent then receives a reward, RT plus 1, out of a whole set of rewards based upon a new state of the environment. And so the environment is now in a new state. There's a reward associated with being in that state. And that was caused in part by the selected action. So this reward then is a function of the previous state and the action the agent took in that state. Okay. So note that the same action might have different results in different states. Right? So it's a function of these two variables, right? So if S of t is a different state out of that set of states, the same action might have a different result, put us in a different state and get a different reward as a consequence of that. And fine, okay, E48. Also note the implication that there may be unmodeled external and random effects that affect the next state of the environment. So we don't always go to the state we think we're going to, where this reward is a function of the new state, right? So we might get maybe a different reward because the reward is that state because we went to a different state than we thought we were, right? So we typically need to model this in a probabilistic way. The state that the environment will enter and the reward the agent will receive are both random variables. So the sets of S and R are finite, so we can define the probability of the transition to state S prime with reward R from taking action A in state S. There's a typo, there should be an E there. That's state, not stat. State S as, all right, so here's some math. Not a lot of math, but it's just kind of declaring this relationship here, right? So there's a conditional probability. So this prior state is, this probability is conditioned upon the prior state being S, some state S in that set, and the action T taken being A out of that state set of actions, right? And now we're looking at this joint probability here that the new state is S prime and the new reward is R, right? So that's how we're forming up this probability distribution. Now consider the time sequence, right? T0, 1, 2, 3, ... So here we have S0, A0, that results in state 1 and reward 1. And then now that we're in state 1, we the agent chooses action 1, which results in a reward 2 and transition to state 2. Now that we're in state 2, the agent chooses action 2 and so on, right? So this is the mathematical representation of the previous diagram on slide 3. Do I still have that right? Slide 3, is that slide 3? Hopefully. That's mathematically, that's what we're looking at, right? So the reward the agent attempts to receive and maximize, right? So it's just greedy. It just wants to maximize its reward, right? So the reward the agent attempts to receive and maximize has been defined for each time step in a sequence. What is the best way to maximize the reward over the sequence? That's a challenge, right? So we generally want to maximize the total expected return, right? So we talked a little bit about this, but we need to do this in a stepwise manner, right? So there's a mouse. He likes cheese. He wants to get to the cheese. That's his ultimate reward, right? But he's got to find his way through this maze to get there. So typically, every time he takes a step, he's using a little bit of energy. So there's a bit of a negative reward, right? He runs into a barrier. Well, there's a big negative reward. Maybe we complicate the game a little bit and there's a mousetrap in some of these things, right? That would be a really negative reward in that game or that episode of the game. Right? So to overemphasize the goal state reward might conflict with the steps needed to get there, right? So if we just overemphasize the reward of getting that cheese, he might just try to go directly there and never get there, right? So again, we use this concept of this gamma as discount factor, and that is again a value greater than or equal to 0, less than or equal to 1, right? So and the because we're raising that to a power in this infinite summation, then that a number less than 1 raised to a power is even smaller, right? It gets smaller and smaller. So this infinite series, even though it's an infinite series, has infinite number of terms, will converge to a finite value. And so here's all our rewards and for our goal state, right? So all right, so I'm going to be a little bit repetitive. Some sequences are finite, like the mouse in a cheese game, right? So run it once and it eats the cheese and we're done, right? If there is a final time step, then the sequence from t equals 0 to t is called an episode, and the system is episodic. Other types of games are continuing and never end. In other words, this t in this range here, t0 to t, that t is infinite, right? So it's just maybe a single game that never ends. But fortunately, with this discount factor less than 1, we can heavily weight the near-term returns, but still account for farther out returns, right? And we can adjust this depending on how close to 0 versus how close to 1 this is. If it's close to 1, then we're going to be this number is still going to stay large, so we're including more and more future rewards. But if it's small, then these will be small with respect to our near-term rewards, right? So if it's close to 0, we'll emphasize the near-term rewards. If it's close to 1, we'll emphasize the total reward. All right. So we talked about policy before. Now we're going to look at it here in terms of reinforcement learning. So we introduce a relationship between states, actions, and rewards with that function there. So how do we determine this function f, right? So given the state t that the environment tells us it's in, how does the agent choose the action, right? So how do we determine f? How do we work with it? Well, before we get into that in a lot of depth, you know, we're going to look at exploration versus exploitation. When we start, we don't have any information on how to act. We haven't figured out that function. We haven't figured out that policy yet, right? So we must explore. We just got to take a step, and hopefully we get some reward out of that, right? But and we would call that exploration, right? But as we learn, we want to actually reap some of the rewards so that we exploit more often. And so that would be exploitation. Once we figured out this function, we'd want to use it to maximize our reward, right? So exploit it. So we can use this thing called greedy epsilon. So we sample from a uniform distribution at each step. Each step we sample from a uniform distribution, and we compare that to some epsilon. And if we're greater than that epsilon value, then we might exploit. If we're less than, we might explore, right? So it's just kind of doing it randomly. And we can modify or increase epsilon during each episode so that as we learn, we tend to do exploitation more often than exploration. Right? So I guess I gotta get that comparison right. But yeah, if you increase epsilon, then more often your random number would be less than epsilon, and so you would, if it's less than epsilon, you would exploit. All right, so I'm gonna just jump through a couple of these things. So we'll come back to these next week. But we're looking at state value function. We've got this policy pi, and we want to come up with the pi that maximizes this value, of being in a state, right? So we want to look at expected return or cumulative rewards starting from the state S and following policy pi. And, slightly different action value function, expected return starting from S, state S, following policy pi, and then taking action A. All right, so we'll look into that. I'm going to we'll talk about Bellman optimality equation. Also, this tells us how we're going to update our policies as we explore. And we'll go into this mathematically next week. But basically, we will go through and explore a little bit. We'll get some reward. So we'll know the state that we've been in. We'll know the action that we take, and then we'll get a reward on that. And then we're going to build this Q table of states and actions and state and action pairs. And we will update this based upon the rewards that we get. But we'll do that with a little bit of a learning factor each time. So as we encounter the same state and take the same action again at some different episode, and we get a different reward that time because it's a bit of a random system, right? So we'll not just completely replace that value, but we'll update that value, right? So Right. So let me real quick, just because I feel like we should do practical things sometimes, right? So let me show you this reinforcement learning type problem here. So again, this isn't Python. This is using Jupyter Notebook, and it's just kind of a nice environment that you can work in. If you've worked with cells and MATLAB, this is very similar. So we can run these individual cells separately and in order, and we'll get some results. Hopefully I'll get the same results now when I do it again. It maintains some memory as you run cells. So I'm going to restart my kernels here. And the first thing we're going to do is we're going to import the NumPy or NumPy library as NP. And this helps us work with matrices and do all sorts of numerical analysis, right? So if you do any data science or machine learning work in Python, you're almost always going to be using NumPy here. We're also going to import Gymnasium. It used to be called Gym. OpenAI developed it. They kind of took their part of it internal, and so there's a fork of it out there that's now called Gymnasium. Right. So, but we'll import Gymnasium as Gym. And what this is this is a virtual or synthetic environment. And so in reinforcement learning, an agent explores an environment. Well, we can create that environment in this Gymnasium. So we'll create different games and have rewards associated with them. And then we can use that as an environment. And then we'll also import matplotlib as and pyplot package within that as PLT, so we can do some pretty plots. And then finally, we'll import pickle. Pickle is a way of serializing an object. Python is an object-oriented language, and so we can take a value and we can save it. An object and save that to disk and then read it in later. So that's called pickling. I don't know if you can hear my dog barking in the background, but I apologize. He didn't come in during the break. So, all right. So now we're going to define a function here, and we're going to call that run. This isn't absolutely necessary. It's just the way this thing is set up. We can run this as an application. And so we'll have a run method of this application. We're going to be able to pass it some values, which I'll describe here in a little bit. But the first thing we do is we're going to play this game called Frozen Lake. And Frozen Lake is, let's see, do I have something like that still? Yeah, so Frozen Lake is this game where we're going to start up here in the top left corner, and we're going to try to get this present down here. But there are some holes in the ice. And if we fall through there, we're going to die, and the game will be over. But the game's over if we get through this maze and get this package. And but each step is going to cost us some energy, right? And we generally want to get to our result as quickly as possible. So if we give us a small negative reward for each step we take, then that incentivizes us to take as few steps as possible to get there, right? So we want to explore this and figure out how to get there. Now, there's some variations on this, in that you can make this ice slippery, and that adds a random component to it. If it's not slippery This game starts the same way. Ice locations in the same spot, the president in the same spot, the same starting spot. So it doesn't take you long to learn this, even if you don't even know what you're doing. Even if you don't even know there's a president over there, you're just maximizing your reward. You'll figure it out after a few episodes, right? And then you can just do it. But adding that slipperiness to it adds a lot of randomness, so we can explore that. Keep an eye on the time here. So we're going to load that game. We're going to make an environment from Jim with this game. There's a bunch of other games in there too, right? And we're going to say it's a 4x4. You can also do an 8x8. That takes longer. We've got a flag here to determine whether it's slippery or not. This is a little Python idiom that we'll just learn on the fly here. So if you want to set a variable according to the value of another variable, so I pass in slip into this function. My default value is true. So if I don't specify it, slip in when I call it, slip is going to be true. But I can set it to true or false. So if it is true, then slippery will be set to true. Else, it'll be set to false, right? So I'm going to say also, this one's a little bit more interesting in that, let's see, do I have a scroll bar here? Yeah. I'm also set up a render mode. This is human mode, and it's nice and pretty, but it's also kind of resource intensive. And so we can either set it to none, so it doesn't do any rendering, or we can set it to human, and it'll do this pretty stuff, right? And again, I set a pass in a flag here of render equals false by default, and so that gives me that, right? So now let's try to go through this quickly so we can see some results. So in reinforcement learning, we're going to either have a training mode or just a do mode, right? So because in training mode, sometimes we're going to explore, but once we've learned that policy, we just probably want to exploit it all the time, right? Not every case, but a lot of times we'll just have this flip-flop here, right? So I'm going to have this Q table that I'm going to initialize to all zeros. And I'm going to use NumPy to do that. It's NP, I'm going to call zeros. And this environment is going to give me back this observation space and the action space. So the observations are going to be what I observe and which thing I'm in, and then the actions are ability to move left, right, up, or down. Okay. And so I get a matrix of zeros, initializes zeros of those dimensions. I'm going to have a learning rate, discount rate, and then here's that epsilon type stuff I was talking about with the exploit versus explore. And now I'm going to do some number of episodes, right? So it might be 1,500 episodes. Actually, I'm going to, so I go through this real quickly. I'm going to do this epsilon check. So I'm going to get a random number. If it's less than epsilon and I'm in training mode, then I'm going to explore the space. I'm going to call sample out of this action space, which could be up, down, left, or right. I'm going to sample that randomly. I'm going to, it's a uniform distribution, so I'm going to randomly choose one of those as my action. Else, right? Else, if I'm not in training or my random number was larger than epsilon, larger than equal to, then I'm going to exploit. I'm going to go into my Q table. We'll talk about this next week, and find the best action to take. And then I'm going to take that action and get it, and I'm going to update my Q table based upon the rewards I get. So let me run these real quick. I'm running out of time. Got 5 minutes. I can do this. So now I'm going to start this running. I'm going to run this 15,000 episodes. So that's not too bad. And I'm training it, but I've set the slipperiness to false. And I didn't render it. But I do get this plot of rewards. You see, as we do episode after episode, by the time we get out to 9,500 or 10,000 episodes, we're getting the best reward. The best reward is we're just getting that present every time, right? So now that was in training. Now I'm gonna run this in a just exploit mode. I'm not going to train at all, right? I'm just going to do 1,000 episodes, and we see that real quickly. We figure it out, and we start getting all of our rewards. So now I'm going to run one, but I'm going to turn render on, and where did it show up at? I think it probably showed up on my other screen. Yeah, okay. So do I have any time left? Let's turn slippery on. And this takes a little bit longer because sometimes it slips. And so you see that it struggles a bit more. It never really gets perfect type of thing. And so here's this guy moving. And so he's normally he would come down here and go right for the present. But he does that so fast we can't see it if there's no slipperiness. Now there's slipperiness, and so he's struggling. Oh, he just died. So it's showing you that he got really close, but he slipped, right? So then he died again. So it gets hard. And he's dying again. So so that's just super real quick practical approach at reinforcement learning. So we're going to call it there, and I will see you next week. So make sure you touch base with me one way or another about your project updates. Get caught up on all your homework assignments. If you're not sure whether you've got all your assignments in, contact me. I'll let you know. And start getting your newer research reviews in. So it's a lot, I know. Semester is going to get crazy from here on out, but we'll get there. I'll moderate the assignments a little bit to keep things under control. All right, so we'll see you next week.
Thank you.
Thank you.
Thank you, Professor.
You're welcome.